So hi guys, today we are going to do lab 1 for robotics subject, which is pick and place motion using Puma 560. So at first we will open the MATLAB apps at this PC, and then we need to wait for the loading. So after a long time of waiting for the loading just now, when this interface appear, we need to click for the new script, and then this space will come out. So we will write the coding as have been shown in the lab manual just now. We have written it before this, so we just copy and paste here, and then we need to run, and then we just save the coding there, and then this will appear.
Okay, so in this experiment, the objective is to control the robot to perform a pick and place operation by using the 3 key position, which is pick position, intermediate position, and place position. So the pick position refers to the initial location where the object is located, which is initial. So the robot is programmed to move it and the effector to this position to grab the object securely. So the next is the robot moves to the intermediate position, which is this position, act as a transition point to ensure safe movement by avoiding the collision and maintaining a smooth trajectory between the pick and place location. And the last one is the robot proceeds to the place position where the object is released at the desired destination. So this already complete the 1 full cycle, which is the pick and place task. So these 3 positions are defined by using the coordinate value, typically in form of x, y, and z, to ensure precise and repeatable robot movement.
So basically, for this experiment, we use MATLAB with the Puma 560 simulator as our main tool. Why does we use the simulator? The simulator allows us to control the robotic arm using joint angle sliders, which makes it easier to visualize the robot's movement in real time. We choose this tool because it helps us understand the relationship between joint variable and the end effector position more clearly. In addition, MATLAB allows us to perform forward kinematics calculation, which we use to validate the position obtained from the simulator. Overall, the simulator is useful because it combines both visualization and mathematical analysis in one platform.
Okay, so guys, now I will demonstrate the system operation of the robot. So first, the robot moves from its initial position to the peak position. So at this point, the end effector activates to grab the object securely. So we need to change this Q2 to negative 30. So we change from negative 30, and then the Q3 we change it to negative 135. Okay, and this is the pick position. Okay, so after picking the object, the robot will move smoothly to the intermediate position. So this step ensures that the robot avoid any obstacles and maintain a safe path during movement. So we change from the peak position, we need to change to the intermediate position. So we need to change the Q1, which is 142.5, and then for Q2 37.5, and for the Q3 is negative 165. Okay, so this is the intermediate position. So we continue to the robot. We continue to the place position. So once it reaches to the position, the end effector reaches the object accurately at the design location. So we change the Q2 and Q3 only. So Q2 is 30. Oh sorry, Q2 is negative 30, and for Q3 is negative 135. Okay, so as you can see here, so the movement of the robot follow the predefined coordinate and it is executed in a controlled and sequential manner. So this demonstrates the system is able to perform the pick and place operation efficiently and accurately. So this complete one full demonstration cycle of the robot system.
Hello guys. So for today we are going to validate our calculation using the homogeneous transformation metric HTML. So first of all, what you need to do is just construct the coding that has been given in the lab manual. But what you can change is that the value of the theta. Here is where you have to change it to the value that you got from the first simulation. And after you're done with that, with all of that over the coding, and also I forgot to mention that you have to put this additional coding to calculate the value of x, y, and z. So let's run this coding and wait up. So here is the output of the coding itself. So you will get the value of the x, y, and z. So based on this value, we can say that the value is same as the value from the simulations. Okay, this part we done with the peak. Now we move on to the intermediate. Based on intermediate, it's just same coding, but again you have to change the value of theta. Here is based on the simulation. So and then just run it, then you will get the value. Forgive me about this. So here again you got the value x, y, and z. So based on this value, I could say that it is the same as the simulation's value. So it's valid. So let's move on to last part, is the place. So here is the place part that you have. Again, you have to change the theta value, same as the simulations one, and then you run it. So you will see the value of x, y, and z. So the value is still the same as the simulation ones. So it is valid. Alright, that's all from me. Thank you.
So, during this experiment, we faced several challenges. One of the main difficulties that we have faced during this experiment was selecting suitable joint angles to ensure smooth movement between the peak, intermediate, and place position. Sometimes, the robot configuration caused unnatural movement or potential of collision. Another challenge was ensuring that the calculated and effective position using forward kinematics matches the simulated results, as small errors in joint values can affect the final position. For improvement, we can enhance the project by implementing automated path planning instead of manually adjusting the joint angles. Additionally, we can improve accuracy by refining the MATLAB calculation and exploring inverse kinematics for better control of the robot's movement. Overall, this experiment helped us better understand robotic motion and kinematics in practical application. That's all from us. Thank you.